In this section, we're going to go through a bunch of different properties of matrices, and then we're going to be able to extend this idea to help us solve those systems of equations. So we've got a lot of properties with real numbers themselves, but now when I've got these columns and rows that all have different numbers, how can I perform the same type of operations? So first, we want to talk about when two matrices are equal. The only way that can happen is if they're exactly the same dimension, so they have the same number of rows and columns, and the corresponding elements are exactly the same. So let's go ahead and look at this example. We want to find the values for the variable which will make the matrices equal. So we've got a variable w here, and it's corresponding to that first row, second element. So that immediately tells me that w has to equal 5 because these two better equal each other. If I look at some of these other pieces, these are all constants and these are all constants and they match up. So I'm going to have to go ahead and go through the remaining process to find what x, y, and z are. If I look at x, it better match up with the first row, third column. So immediately I get that x has to equal 6. If I move on to where the y value is, it's the second row, third column. So this expression better equal 0. So I get y plus 2 is equal to 0, which tells me that y is equal to -2. And then finally, if we move on to z, that's in the third row, third column, better be the same exact thing in the third row, third column over here. So that tells me that z has to equal 8. Okay. So now when I've got matrices that are the same order, so they're the same size, we can perform operations like addition and subtraction. And we have a couple different types of multiplication. So first, for general addition, you just go ahead and add those exact corresponding elements together. So to add or subtract matrices of the same dimension, that being a key, if they're different sizes, I don't have the same corresponding elements, so I can't do that. You're going to go ahead and just add those like components or those like pieces. If we want to multiply a matrix by a number, then I'm going to go ahead and just distribute that number to every single element of the matrix. When we get to a different type of matrix multiplication, it's going to be a little bit more complicated. So when we take the product of two matrices, we have a process we have to follow. So first, let's start with the sum or difference and that simple matrix multiplication. So I want to go ahead and add these two matrices together. This first one is a 2 by 3 matrix. The second one is also a 2 by 3 matrix. They're the same size, so we can go ahead and add them. So I'm going to get a matrix of exactly the same size. So the first time, for my first row, first column, I'm going to add these like components together. So I'll get 6 plus -8 in this position. So we'll go ahead and actually do that algebra each time. So I'm going to get -2 in that first row, first column. If I move on to my first row, second column, those like pieces are -9 and 2. So we go ahead and just add those together. So in the first row, second column, my value for the addition will be -7. If we move on to the first row, third column, we'll get a 2 plus a 5. So the element here will be +7. Then I move on to the second row, first column, we've got 4 plus 6, so that's going to give us +10. Then we move on to the first or second row, second column, which is 1 plus -3. So the element that'll go here in the addition will be -2. And then finally, in my second row, third column, I've got a 3 plus a 4. So we're going to get a +7 in this piece here. Now if I want to subtract, same thing. They're both 2 by 2 matrices, so I just subtract the same type of components. So I'm going to combine those first row, first column to get 2 minus -1. If I move on to the next element, I've got the square root of 7 minus 5 root 7. So we'll be able to simplify that. Then we've got 3 root 28 minus 2 root 7 in this position. And then we've got -6 minus 2 in this last position. So now it's a matter of just going through and actually performing each of these subtractions. 2 minus -1 is 2 plus 1, so that's 3. If I take root 7 and I take away 5 more, we've got -4 root 7. Now I can't combine the square root of 28 and square root of 7 right now, but I can break down that 28 into something that deals with a perfect square. So we get the square root of 7 times 4 underneath that radical. So we'll be able to break that down a little bit further. But then -6 minus 2, just a -8. So all of these 3 pieces are already finished, but now that square root of 4 will turn into a 2, so we're going to get 6 root 7 minus 2 root 7, and so that will become +4 root 7. Okay. And now in this one, I've got the matrix 4, 6 minus 2, 3. But here we have a bit of a problem. So this is a 1 by 2 matrix, and this is a 2 by 1. So we can't actually add or subtract these. They're different size matrices. So this operation we can't do. Now in this one, if I want to take -2 and multiply it by a matrix, all we're going to do is multiply every single element by -2. So it's just going to double and change the sign. Okay. So that is our first way we can multiply with matrices, but that's with a scalar out front. So it's just a real number times a matrix. But now if I want to multiply 2 matrices together, we've got a more complicated process. And there has to be very specific sizes to be able to multiply them. Say you have one matrix that's an m by n. It can be multiplied by a matrix of a different size, but the number of columns of the one has to match the number of rows to the second. And what you're going to get then is a matrix of dimension m by p, or order m by p. So what that means, let's actually look at an example, and this is going to be the best way to actually go through our process. Let's multiply A times B, and we've got this matrix A, this matrix B. This matrix is a 2 by 2. This matrix has 2 rows, 1 column. So here, this inside piece is the same number, so I can actually multiply them together. So these two have to match up. And then the order I'm going to result with will be what these n pieces are. So it will result in a 2 by 1 matrix. If this was a 3 by 2 and a 2 by 1, you would get a 3 by 1 matrix in return. Now to actually perform the multiplication, each element in that 2 by 1 matrix will be found by utilizing every single row and every single column. So first, to find that first position, I'm going to locate the first row of my first matrix and the first column of my second matrix. We're going to multiply the corresponding elements, so the first one in the highlighted thing, the second one in the highlighted thing, and add them together. This will be the element that will be in the first row, first column. So it matches exactly those same locations. So I'm going to go ahead and I'm going to multiply the 1 by -1 because they're the first piece in that first row, first column. So this will be my first part. And I'm going to add to it the next elements multiplied together. So 2 times 7. So that's going to give me -1 plus 14, which will result in positive 13. So that's going to be the first piece in my 2 by 1 matrix. To get the second element that's in the second row, first column, I'm going to go ahead and locate row 2 and column 1 of my matrix. So here's row 2 and column 1. And I want to do the same type of thing. I'm going to multiply those corresponding elements. So I take the first thing in my highlighted row, multiply it by the first thing in my highlighted column. So that's going to give me 3 times negative 1. Move on to the next number and the next number. So we're going to add to that 4 times 7. So this is going to give us negative 3 plus 28, which is 25. So the product of these matrices then is I took this first row, first column, and when I multiplied those, I got 13. When we took the second row, first column, multiplied those together, we got positive 25. So this is our resulting 2 by 1 matrix. Okay. So let's try it again with a bigger matrix. We're going to do the same process. If you look here, this has 2 rows, 3 columns, so it's a 2 by 3 matrix. This one has 3 rows, 2 columns, so it's 2 by 3. We can go ahead and multiply these because those insides match up. And so the result will be a 2 by 2 matrix. So I'm going to go ahead and give these matrices elements values, so this way you can kind of see where we're coming up with each value on its own. So to find this first position, we're going to go ahead and look at the first row and first column. So my first row, first column, the A11 spot. Okay. So we're going to multiply those like pieces. You've got the 1 times the 1. We're going to add to that the next piece, which is 2 times 0. And then the last piece, which is negative 1 times 3. So this just gives us 1 plus 0 minus 3. And so the element that'll go in the first row, first column is negative 2. Now to move on to my next piece, which is A12. That 1 stands for the first row, the 2 stands for the second column. So I'm going to go ahead and locate the first row and the second column, and we'll repeat this process of multiplication. So the A12 element will be I multiply the first piece in each, so that's 1 times negative 2. Then I multiply the next 2 together and add that, so 2 times 1. And then finally, the last piece, which is negative 1 times 5. So this gives me negative 2 plus 2 minus 5. That just equals negative 5. Now to do my third element, which is my second row, first column, I'm going to go ahead and locate these. So the 2, 1 position deals with the second row, first column. So this element will be multiplying the first together. So 4 times 1. Add, multiplying the second, which is negative 3 times 0. Add, multiplying the third, which is 2 times 3. So that's going to give me 10 overall. And then finally, the last position that we have to find is A22. So that's the second row, second column. So within both of these, I'm going to look at the second row in the first one and the second column, and this will give me A22. So I go ahead and multiply the first to give me 4 times negative 2, then the next one, which is negative 3 and 1, and then finally 2 and 5. So overall, this element will be negative 1. So now I go ahead and the product of these will be negative 2, negative 5, 10, negative 1. So anytime you have these matrix multiplication, that specific position will deal with the blank row of this first matrix and the blank column of this. So if you had like a 3x3 matrix, as a result, to find the third row first element, you would look at the third row in your first matrix, the first column in your second matrix. But one of the big things here that's kind of different, normally when you switch order of multiplication, 2 times 3 is 3 times 2. But here the order is important, and in general, you can't switch them. You're going to result in a different matrix. So for example, if I went ahead and switched the order which I multiplied these two matrices in, this first matrix is a 3x2, and this is a 2x3. So you could multiply them because these match up, but the result would be a 3x3 matrix instead. And you'd repeat the same process. The first element in the first column would be the product of these two, and you keep going through it. But the order is very important. You can't just switch them. So pay close attention when you're going through this. But these matrices, again, are going to be useful when you have a lot of information. So we're going to see some more properties in the next section, but we're also going to go through how to solve systems of equations utilizing these matrices and matrix properties.